Welcome back to another video in our course Measure Theory for Probabilists. Today we are going to define the integral in a few steps. We will use so-called simple functions and extend these to measurable functions and define the integral with respect to a measure. We will also connect the measure we are going to define today with the Riemann integral, which you might know from calculus. So let's start. So let's get started and define some integrals. So what is an integral? So here, mu is a measure, f is some function, and that's just our notation here. So measure square brackets function is the integral f d mu, or maybe you write it f of omega mu d omega, where omega is an element from capital Omega. And we're going to define this here for many of these functions f, so for as many as possible. And we will be doing this in basically two steps. So the first is a mini step, so I don't really care about this. So if f here is an indicator function, then define mu of f like mu of a. So in general, let's say mu is Lebesgue measure, such that all elements of the line here get the same weight. And you have a function, maybe like this here. So what is the integral? You weight all the function values according to the measure. And when you do this, and you have, for example, some set A, then this here is the indicator function. And you weight elements outside here with 0. You weight elements within the set A with 1. So mu of f is mu of a. Okay, you probably also heard that integrals are assumed to be linear. And you can see this here in this definition also. So for simple functions. So this here is a simple function. And for the simple function, we just define the measure by using linearity. So mu of f, well, mu and the sum commutes. Mu and a constant commutes. And mu of an indicator, that's just like here. So that's the definition of the integral when f is a simple function. And for the final step, we will need what we had last time on the last slide. Like here, we had that measurable functions can be approximated from below by simple functions. So when f is measurable, we are going to use this approximation from below in order to define the integral mu f. So let's start. So we already have the definition here. So for simple functions, we define the integral. Okay, and for this here, fg are non-negative simple functions. So non-negative means that the ci's here are bigger or equal to 0. Then the integral here is linear and monotone, like this here. And I'm not going to show this because I say that's clear anyway. Yeah. Okay, so these are just simple properties of just finite sums. You can make up your mind why that should hold. So for example, here linearity is clear because you can write another simple function, which is the linear combination of the simple functions f and g. And you can also do it with the right hand side. And see that the sums are just the same. One remark which is probably important. So A here is a measurable set, right? And the indicator function, well, does not need to be piecewise continuous. For example, A could be something like Q, the rational numbers. So, well, I cannot draw this. So the indicator function of Q, I cannot draw this because I need countably many points here on top and I need uncountably many points on the bottom. And between any two countable points, I have one from, which is irrational, and also the other way around. So I cannot draw this, but you know what I mean. So if x, so if the position here is rational, I have a 1. If it's irrational, I have a 0. That's a very irregular function, which is not piecewise continuous. And why am I saying this? I'm saying this because you're used to writing an integral here, probably for f which is piecewise continuous. And that means the indicator function cannot be evaluated using the Riemann integral, which uses these piecewise continuous functions. We are going to define a more general function, more general integral, where we are able to integrate, for example, this indicator function of Q. Okay, next steps. Non-negative measurable functions. Define the integral of non-negative measurable functions. Well, notation is as usual. What are you doing? You define the integral as a supremum of all integrals with respect to simple functions, which are non-negative, which are all smaller or equal to f. So you approximate f from below by simple functions, and we already know that the integral over simple functions is monotone, which means that there must be an upper limit, and this upper limit of all these integrals with respect to simple functions I call the integral of f. And here f only takes positive or non-negative values. That's important. The next case is that f can take, well, any real number. We say f is mu integrable if mu of the absolute value of f, which is a function which goes to r plus, is finite. And how do we define this? Well, we integrate f plus. So did I ever define what f plus is? So f plus equals f maximum 0. So if f is negative, it's 0, and f minus is minus f maximum 0. So f equals f plus minus f minus. And since the integral should be linear, we define mu of f as mu of f plus minus mu of f minus. Okay, that's this definition. And one definition or notation or so, which we will also use, is here the integral of f and then a comma and then a set. And by this I mean the integral over f times the indicator function of a. That's just notation. Yeah. Okay, let's make the first proposition on these definitions. Here I only have functions which take non-negative values. First of all, monotonicity stays. It's inherited from the integral of simple functions, so that should be okay. Linearity also is inherited from the simple functions, so that should also be okay. But I would like to focus on the second property because that's a really important thing, which we will also need later. So if fn increases to f, then the integrals already also converge. So that's I will call the convergence theorem in the next video. And the reason why the convergence theorems for this integral we are defining here are so nice is exactly this statement here. So let's look at this here for the proof. Yeah, so the claim is that the sup over all n mu integrated with respect to xn equals mu integrated with respect to f. Not claim, but claim. So, the mu of fn that increases because the fn's increase in the integral is monotone. And yeah, so we have two directions to show. Smaller equal first. Yeah, so mu fn is smaller equal than mu f. That's pretty clear because fn is smaller or equal to f, and we have monotonicity, and well, that holds for all n, so it also holds for the supremum. So that's easy. The other direction is a bit harder. We need to use the definition of the integral. We are going to show that mu of g is smaller or equal to sup mu fn for all g is smaller or equal to f simple. Yeah. And just for completeness, let's say g of omega is a sum ck indicator of a case k from 1 to m. Then, okay, g is smaller or equal than f, and fn increases to f. Then I can define Bn. That's also choose epsilon bigger than 0. I have to say choose epsilon bigger than 0. And well, I'm going to show that 1 minus epsilon mu of g is more than equal than this here. That's what I want to show. But epsilon is arbitrary. That means I can let epsilon go to 0 here. Then mu of g must also be smaller or equal than the supremum of all integrals. So that's what I'm going to show. The set Bn I'm going to define is the set of omega such that Fn bigger or equal than 1 minus epsilon g. Okay, g is smaller or equal than f. That means 1 minus epsilon g is also smaller or equal than f. And the fn's, they increase to f. And that means that this set here, for all epsilon, increases to omega. And, well, it increases. Wait a moment. It does not need to increase because I have no control over the fn's, but it converges. Well, what does it say? What does it mean to converge here? And what I mean is that the union over all n, the Bn, that's my omega. That's clear, I think, because, well, assume there is a point in omega which is not in the union of the bn's here. That would mean that Fn is smaller than 1 minus epsilon g for all n. Yeah, well, but then Fn cannot converge to something which is bigger than g, because it always stays below 1 minus epsilon g. So like this here. And then I can write the integral of Fn. I can use monotonicity. That's bigger or equal than integral over 1 minus epsilon g bn, I claim, because Fn is bigger or equal than 1 minus epsilon g, at least on bn, and well, on omega without bn I don't really care, because this is going to go away anyway. So like this here, wait, bn here doesn't make sense, but indicator of bn makes sense. This right hand side I can write as a sum, 1 minus epsilon ck mu of, well, bn, and the g also has an ak, so mu of ak intersect with bn. And now if n goes to infinity, the bn goes to b, and the sum here goes to 1 minus epsilon ck mu of ak, which is, okay, the 1 minus epsilon I have to keep. But this here, that's just the integral of mu with respect to g, mu g. So I've shown this here, and that's exactly what I wanted to show. So I'm done. I've shown smaller equal and bigger than or equal. So I have shown equality because epsilon was arbitrary. And we have this nice approximation property from below. Okay. One notation I will need. I will also need that more general also in the next chapter. So L1, the so-called space L1, is the set of functions from omega to R bar such that mu integrate f bar to the power of 1 here without between that's finite. So that's the set of all functions which have finite integral. And next chapter will be a p here, not a 1, and here a p also here. So these I will call LP spaces. Yeah, some properties. Okay, monotonicity. Now it's a bit different. F almost everywhere. So it means there's a null set such that F can be also bigger than G. But only a null set. And then mu of F is more equal than mu of G. In particular, what we will need frequently is this here. So F is more equal than absolute value of F. And that means, yeah, that the inequality holds without these two signs. But the same holds for minus F. Minus F is also smaller or equal than absolute value of F. And that leads to this inequality, which is used often in some bounds. Linearity, that's clear because it's also inherited from the simple functions. And the fourth is something which we need in probability theory. So when you have an f, you have the image measure of G under this image measure of f, then that's the same as integrating the composition of G and f. Well, that looks as if you can prove something. Let's prove it for G simple. Yeah, for G simple. G, oh, that's right. G equals sum over CK indicator A1K, AK. And G by F, what's that? That's again the CK sum over not AK now, but the indicator that F is in AK. Well, and now I can write mu G by F. And by the way, this here is also a set in my sigma algebra because F here is measurable. F must be measurable because I wrote down here the integral, and the integral I can only write down if the integrand is measurable. So what's this here? G by F, I have to use the sum CK mu of G by F, I integrate this here, mu of F in AK, F in AK. But F in AK, okay, what's that? CK, that's F stay bar mu of AK, which is in turn F star mu, and I integrate my G by definition. That means the formula holds here for simple functions, G, and by approximation, again, I can use also general measurable functions. Then the next property. Properties almost everywhere. So f again goes only to the non-negative numbers. And I have that f is 0 almost everywhere if and only if the integral is 0. And if the integral is finite, then f is almost everywhere finite. Let's show this. So I define the null set N, which is the set f bigger than 0. That must be measurable because we had also last time that f smaller or equal than x is in f, and the complement is also in f, so f bigger than 0 is in f because f is measurable. And for 1, I have two directions. If f is 0 almost everywhere, then the integral is 0. First of all, the integral is non-negative because f is non-negative. Here I can write that's the same as the integral f comma n, because on non-n f is 0 anyway, and f times the indicator function of n is the same as f itself. I have this here, if fn grows to f, then the integrals converge. I have that's the same as the limit mu integrated against f minimum n on n, so on the null set n. This here by monotonicity is smaller or equal than mu of n, comma, capital N. Well, so a constant, it's easy to integrate a constant, that's n itself, and mu of n is 0, and the limit n goes to infinity of n times 0, n times 0 is 0, and the limit n goes to infinity from n is 0 again. So that's one part. And the other way around. I need n, index n, is the set f bigger or equal than 1 over n. This here increases to my set n as before. And nf is bigger or equal than indicator nn. Why is that? Okay. N times f on nn is bigger or equal than 1. And outside nn, well, it's bigger or equal than 0 because f goes to r plus. So this here holds true. And now I can write, well, I do know that mu integrated against f, that's 0. I know this by assumption. And f is bigger or equal than 1 over n indicator nn. 1 over n, integrate the indicator, which means mu of nn. And that's 0. Yeah, that must be 0. That only works if nn has measure 0. Mu of nn is 0. And so I can conclude by subadditivity, mu of n is the union of the nn's, limit mu of nn's. All of these I have measure 0, so the limit is also 0. That was the first claim. And the second, that was here, if the integral is finite, then the function itself is almost everywhere finite. First, f equals infinity, that's a set which I call A. And I have f times the indicator, f bigger or equal than n, is bigger or equal than n times the indicator function, f bigger or equal than n. And then mu of A, that should become 0 because f equals infinity, well, can happen only on a set of size 0. So mu of A, we have to prove that's 0. That's mu integrated against indicator of A. A is the set where f is infinity. If f is infinity, it's certainly bigger than any small n. That's integrating this function here, so that's smaller or equal than f divided by n, indicator f bigger or equal than n. So 1 over n mu f, indicator f bigger or equal than n. Okay, now I can make that even bigger if I ignore the indicator function here. By assumption, mu f is finite, and this finite number I divide by n, which becomes larger and larger. So this one here certainly goes to 0. Here n to infinity goes to 0. Well, and this here does not, so what we want to see, it doesn't depend on n at all. That means mu of a must be 0. And we have this property. Okay, let's now come to the connection of the integral we just defined by the so-called Riemann integral, which you might know from your basic calculus course. The Riemann integral is almost the same on paper. The only difference is that you have usually just a line. You want to integrate something from 0 to t. And you do that by doing steps. Yeah, you have steps between xj minus 1 and xj. That's just some partition of the interval 0 t. And if you have piecewise constant functions, well, the function which is piecewise constant, so like this, for example, piecewise constant, then the integral is again similar to what we had for the simple functions. But here, the main difference is that the indicator here, that's here really an interval. And for the simple functions, we had some measurable set here, which is much more general. Yeah, so that's piecewise constant function and the integral for this. And the general function is Riemann integrable. If, well, its absolute value must be integrable to something finite. And there are piecewise constant functions, yeah, approximated this by from below and from above by fn minus and fn plus. Their difference must integrate to 0. And then, what I claim here, the Riemann and Lebesgue integral then coincide. That's then clear because all these here, they are in fact measurable sets. And that's what I can use for the Lebesgue, for the other integral, which I call here now the Lebesgue integral. And sometimes for the Riemann integral, you even are a bit more general. Here, what you usually do, well, we do not consider functions from R to R, but for example, from 0t to R, to R, and then continue and so on. And if this set you want to integrate over is not compact, but unbounded, then you say f is Riemann integrable. If it's Riemann integrable for all compact intervals k. Yeah. And then you say, well, that's a compact set, minus n to n, and you let n go to infinity. That gives you the integral of f with respect to Riemann. And, well, there are connections between Riemann integrability and integrability in the sense that we had on the first few slides today. Yeah, and here's one connection. So you have a piecewise continuous function. You are having these points on the x-axis, so this partition xn0 to xnkn, which becomes finer and finer, and which contains the y and k's. And here the weighted average f of y n k x n k minus x n k minus 1. This here converges and gives me the integral over f. Well, and for the proof, I do not want to say too much, actually. Again, the main thing is that you have just more general than these functions here when you define the integral in the first place. And we can use the techniques from there. So we can find simple functions which approximate the function f here from below and from above. And then get exactly the same as in the Riemann integral case. Yeah, so there's a deep connection here between Riemann and Lebesgue integral, which we can then use because they coincide. So let us come to two examples. The first one is a function which is not Riemann integrable, but Lebesgue integrable. And for the second function, it's the other way around. So we already discussed, for Riemann integrable, we need something which is piecewise continuous at least. And the indicator function of q, or q intersection with the unit interval, that's not a piecewise continuous function because it jumps all the time. So that's not Riemann integrable. But it is Lebesgue integrable, as you will see in one exercise. You can also compute the value. For the second example, we already saw that Riemann integrable functions are always Lebesgue integrable, with one exception. And the exception is well, here is the thing. So you define the Riemann integral only on compact sets, and then you let the compact set grow to the whole set and define the Riemann integral by this then. And we can do this, for example, for this function here. So let me just draw this. If t is between 0 and 1, I have here 1, and I have here 1, so that's 1. Between 1 and 2, I have a 2 here, and I have a minus here, so that's the minus a half, then it comes plus a third, minus a fourth, plus a fifth, and so on. So that's the function. Of course, the absolute value of this here is 1 over t, which is not integrable. So this here holds. And that's the reason why this f here is not integrable, because the Lebesgue integral can only be defined on functions which are also, where also the absolute value is integrable, and that's not the case here. But if you evaluate the integral over a compact set, so 0 to 2n, for example, you can have this here. That's just by definition. And when you write this down, I mean, we just went through all the values. 1 minus 1 or 2, plus a third minus a fourth, plus a fifth minus a sixth, and so on. So what you're doing is 1 over an odd value minus 1 over the next even value. So something like this here. And you do this here for the first n pairs of odd and even values. So that's the reason for this sum here. I can write it differently because I can find a common denominator. And I have this here. And basically that's something like 1 over k squared times some constants and a bit shifted. But that means here, if n goes to infinity, that goes to a c which is finite. And that c here, well, this is then the Riemann integral over this function f. And this function f is therefore Riemann, but not Lebesgue integral. Okay, so much for today. Next time we will discuss convergence theorems for the integral we defined. See you then.